Hello everybody, this is Unit 1, Atomic Structure, Section 3, Electrons in an Atom. So you should have out in front of you your guided notes for Section 3. We'll try and keep it pretty short and sweet for this, but this is a really important section, and in order to fully understand this, you really kind of need to know the difference between the nucleus and the energy levels / electron cloud, and you really need to have a good handle on those charges and things for the subatomic particles. So make sure that you thoroughly understand Unit 1.1 and 1.2, which covers all of your subatomic particles, protons, neutrons, electrons, mass number, average atomic mass, all that jazz. So as you guys can see, we've got a ton of really cute cartoons that I'm really excited about. And one of my favorite things is to do all these chemistry or science jokes, but I need to get you learning some chem before I can throw down all my awesome chemistry jokes on you, but they're coming. Oh, don't worry, they are coming. So far this year, we've been focusing a lot about what's happening inside the nucleus. What is going on with the protons and the neutrons? What happens if the nucleus is unstable? All of that radioactive decay stuff, all of the nucleus breaking down into the alpha particles or the gamma particle or the beta positive or beta negative decay. But that's really only talking about the nucleus. Those are very specific cases. Most atoms are not unstable. Most atoms do not have wonky things going on with radioactivity. So we're going to kind of take all that radioactivity mess, we're going to take all that unstable nucleus mess, and we're going to put it off to the side, because most of our year is centering around chemical reactions, and chemical reactions happen because of the electron. So this is honestly one of the most important sections, because the rest of chemistry, other than nuclear stuff, relies on our understanding of electrons. So in order to function properly, atoms must organize electrons so they don't collide. Remember, when we talked about the quantum mechanical model, we said that electrons are all negative, and two negatives don't want to be too close together. That's just like magnets. If you put the north end and the north end of a magnet together, they're going to repel. So we need the atoms to organize their electrons so they don't collide, because they're all repelling each other. Electrons want to get as far apart as possible. And in order to do that, we put these electrons inside those energy levels, with the outermost electrons in an atom being called our valence electrons. So that very, very most outer shell, our outer energy level, whatever that is considered to be our valence energy level, and any electrons in there are our valence electrons. And remember, we talked about how those are going to be the really important ones, because those are the ones that cause the bonding to happen from one atom to another atom, which is really why we exist. When we get two atoms bonded together, we can make bigger atoms and bigger molecules and bigger compounds and things like that. Our whole existence is based off of valence electrons moving around from one atom to another one. But that's a little too deep for what we're going into today. We're just talking about the fact that they exist. Cool. Electrons in the outermost energy level are our valence electrons. We're going to get deeper into this whole mess at the end of this unit. But really, we just need to know that energy levels have kind of these set distances from the center of the atom, and we've shown the energy level 1, 2, 3, 4, all the way up to 7. You saw that on your quantum mechanical model sheet when we did our atomic models. Each energy level can contain a specific number of electrons. You don't need to memorize that number. We're going to do stuff with that later on. So I'm not even going to tell you how many electrons each energy level holds, because you don't need to memorize it. But you should know that the closer you are to the nucleus, the smaller the energy levels are. And if they're smaller energy levels, then they've got fewer sublevels. If they have fewer sublevels, they've got fewer electrons. That should kind of make sense. If I have a smaller space, I can't put as many electrons there. So we're going to do a really fun lab where we take electrons from what we call the ground state, and we're going to excite them. It may be a exciting lab. Yeah, I went there. So the normal place where an electron would be is called its ground state. So wherever they're at naturally, that's where they are. But remember, we talked about how electrons can move up or down those energy levels. If an atom absorbs energy, then the electron's going to move up. Remember, higher energy levels have higher energy. So if the electron gets more energy, it's got to move up an energy level. So if we throw energy at an atom, such as heat or light, then electrons can jump up to the next energy level. We consider that jumping up part, when it jumped up to the next energy level, it's called its excited state. Electrons can't stay at that position though. It's really hard for them to stay at that position. They will eventually drop back down to their ground state, to their natural state. So what goes up must come back down. When they fall back down, they have to release off that energy. Remember, they're placed in their energy level based off of how much energy they have. So when they gain energy, they move up energy levels. When they lose energy, they move back down. The cool part about this is that when the electron falls back down to ground state, that energy it gives off comes off in the form of a photon, which is traveling light, or in the form of radiation. This is one of my favorite science jokes, and I will tell you this joke about 15,000 times, so strap in. This should all be fairly review for most of you. I know that a lot of you talked about this in 8th grade or in bio or in earth science. You talked about the electromagnetic spectrum. And the electromagnetic spectrum is really the spectrum for all the light, even the light we can't see, including radio waves, gamma rays, X-rays, all that kind of stuff. We can actually only see a very, very small portion of the electromagnetic spectrum. And this shows us a list of the electromagnetic waves in order of decreasing wavelength. So you can see with our decreasing wavelength, I'm going to get out my pen here, we have shorter wavelengths up here with our gamma rays, and when they have shorter wavelengths, meaning they're closer together, those are going to be our high energy waves. Remember, gamma radiation is like the radioactive Chernobyl-y radiation, the bad radiation that we think of. And visible light, that's not going to harm us. We have a smaller, or I'm sorry, not a smaller, we have a slightly larger wavelength there. And then when we get into the really large wavelengths, we get into our radio waves, which have really, really low energy. So at this point, you can look at this picture and you can look at the wavelengths of light and see that each color corresponds to a different wavelength, meaning that each color corresponds to a different amount of energy. And we're going to get into why that is important in a couple of minutes. So here's what a wavelength is. Hopefully this is not a new picture to you, but if it is, it's here anyway. So wavelength refers to this distance right here. It would help if I actually had a pen on me. Hold on. Woo. Here we go. Okay, the wavelength refers to this distance from crest to crest, or this one from trough to trough. It doesn't matter which way you measure it, but you need to measure it from the top of one wave to the top of another wave, or from the bottom of one wave to the bottom of another wave. And our frequency here is, our frequency is related very much to wavelength, because you can see that a frequency is really how many crests we have over a given second, or how many crests we have over a given period of time. And if your wavelength is short, like this guy has a short wavelength compared to this guy here, then our short wavelengths have higher frequency, and our long wavelengths have lower frequency. So if we have a high frequency, short wavelength, then we have a high energy. And if we have a low frequency, but long wavelength, then we have a low energy wave. So if we're going to compare these two colors, then the high frequency wave is more likely to be on the blue or violet side of the visible light spectrum, and the low frequency wave is more likely to be on the red or orange side, because red light has low energy. So here's what we were just talking about with that, that each color of light represents a different energy or a different wavelength of light, and we can match those up to actual numbers. You can do calculations for this. We're not going to do them in this class, but you can do calculations to figure out exactly what wavelength of light you have, and you can compare that to figure out exactly what color it is. So if you remember, the whole reason why we're talking about color of light and wavelength and energy is because we can excite an electron, have the electron jump up to an excited state, and when the electron falls back down, it's got to release that energy. And the energy it releases is going to be in the form of light, oftentimes visible light. So it's going to give off a color of light. And that color will change based off of how far the electron falls. Where if it falls further, it's going to give off a higher energy wave because it released more energy. If it falls only a short distance, then it's going to give off less energy and more like a red or orange color. So here's kind of a depiction of this. This is actually one of your practice questions. This is the first practice question, where I ask you to draw an image of a Bohr model of an atom going, and you need to show me the excited state and you need to show me the ground state. So here are two different electrons going through two different states, just to show you the different colors of light. But at one point, this first electron here started down in energy level 2, absorbed energy, and jumped up. So this is the top part here is its excited state. Energy level 2 was its ground state. And after it fell back down, it released a high energy wave or a medium energy wave that corresponded to green light. Whereas this guy here, the second electron, it absorbed some energy, it jumped up to its present excited state, and then as it falls back down, it's only going to fall back down one energy level. It's going to release lower amount of energy, and that's going to correspond to red light. So the further you fall, the more energy you give off, and the higher energy light corresponds to that amount of energy. That's saying energy quite a lot, might be. What's really awesome about this is that this concept can be used for a lot of different things. Each element or each compound actually will give off its own what we call an emission spectra or an atomic spectrum. And what this is when the electrons get excited and then fall back down, they have like a fingerprint to them with the color of light that they give off, because each atom ends up having its own like little specific set of energy level distances and how its electrons go into excited state and grounded state. And therefore, it gets this fingerprint for its emission spectra. And we've actually been able to identify the composition of stars and the composition of the sun and the composition of atmospheres of planets and all sorts of cool things by using the atomic emission spectrums of them. That's how we figured out that helium existed. We didn't find helium on Earth first. We did it by observing the sun, and we observed the atomic spectrum, which are these guys here. And it gave off a new signature that we'd never seen before. And that's how we discovered that helium existed. We discovered it in the sun first. So go ahead, take a minute to summarize your notes in that summary section, and then make sure that you finish the last two practice problems. Make sure that you actually go through and label all of the things in question number 1. That's definitely something that we test on very heavily, so make sure that you understand that thoroughly. I'll see you guys soon. Have a good day.